Next theorem is theorem or lemma. If sequence Sn is Cauchy sequence then sequence Sn is where entrance from 1 to infinity is bounded. So how to prove this lemma? Prove. Okay, statement says that if given every Cauchy sequence is a bounded sequence, that is every Cauchy sequence of real number is bounded. How to prove this? Because every convoluted sequence is Cauchy sequence and every convoluted sequence is bounded sequence. So every convoluted sequence is Cauchy sequence, therefore Cauchy sequence is bounded sequence. In this way, but here how to prove? Here by using direct definition. Okay, here given that sequence Sn is Cauchy sequence is given, and to show that mod Sn is less than some any number, any number m. Okay, so using this let proof of this theorem. Let sequence Sn where entrance from 1 to infinity is Cauchy sequence therefore by definition of Cauchy sequence, for all epsilon greater than 0, sequence Sn is Cauchy sequence, which implies that for all epsilon greater than 0 there exists n belongs to I such that mod Sm minus Sn is strictly less than epsilon for all mn greater or equal n. Okay, positive integer n means here one of the any integer exists such that the difference between two numbers of sequence is very less than epsilon. Okay, so therefore if taking epsilon is equal to 1, which is greater than 0, if we take epsilon is equal to 0, then 1, then mod Sm minus Sn is strictly less than 1. Okay, is strictly less than 1 for all mn greater or equal n, and we have to show that here. What to show here? Given sequence mod Sn is a sequence. Given sequence mod Sn is a bounded sequence. Bounded means mod Sn, to show that this is m mod Sm or mod Sm, whatever may be. Okay, both sequences, this is a m number, this is nth number. Okay, whatever may be, which is a less than some any number. Okay, and therefore by using this consider mod Sm. Okay, suppose that which is considered mod Sm is equal to adding subtracting Sm minus Sn, because m and n are greater or equal n this. Okay, so choosing add and subtract this nth number of sequence, this is nth number of sequence plus Sn. Okay, so therefore which is less than or equal to Sm minus Sn plus Sn. Using this result, mod A plus B is strictly less than mod A less equal mod A plus mod B. Okay, using this result, so suppose this is A and this is B, and this value is strictly less equal in this way. Okay, but distance of two numbers is a very small in sequence, and which is a epsilon. Okay, and here epsilon is taking a, here n is this n is a greater equal n. This implies that n is greater equal n, which implies that this value, distance between Sm and this Sm is must be strictly less than, this is strictly less than 1 plus, because from, suppose that this is equation number star, from star plus mod Sn, okay, by using from star, okay, and their equation number is, suppose that 1, mod Sm is a less than 1 plus mod Sm. So let choose m is equal to maximum of 1 plus mod Sn, 1 plus mod Sn plus 1, then mod Sn plus 2, and up to so on. Choosing this number, suppose we have to choose here, suppose that here sequence is given that 1 to up to 10, okay, 1 to up to 10, then we be choosing m is equal to maximum of 1 to up to 10, okay, and therefore this is, suppose that this number is 1 plus mod Sn, then 2 is mod Sn plus 2, okay, then 3 is mod Sn plus 3, and up to so on. In this way, so first number is suppose that 1 plus mod Sn, okay, or whatever may be, but m is choosing from maximum of all this number, and then clearly here we see that 1 plus mod Sn is must be less than m, because m is a maximum. If 1 plus mod Sn is a maximum in this number, then which is a greater equal m, but if 1 plus mod Sn is a not maximum in all number, okay, in this sequence 1 plus mod Sn is not greater than this all number, then m is a any number, then which is a 1 plus mod Sn is must be strictly less than m, okay. So suppose that this is number maximum of 1 to 10 is a m, because this is maximum in 1 to 10 number, okay, 10 is a greater than all number, therefore m is equal to 10, but 1 plus mod Sn is equal to 10, then m equal to 1 plus mod Sn, but if 1 plus mod Sn is not equal to 10 in this set, then 1 plus mod Sn is must be less than 10, and which is equal to m, okay. So in this way m is a choose from maximum of 1 plus mod Sn, Sn plus 1, Sn plus 2 up to so on, okay, just n plus 1 number, n plus 2 number, and in this way choosing m, then clearly 1 plus mod Sn, clearly 1 plus mod Sn is less equal this m is a any number of in this way, okay, any one of the number of given sequence m, but which is a maximum in this set, okay, and therefore equation 1 becomes mod Sm, this sequence is less equal, so which is strictly less than m, okay, which is strictly less than m, and therefore by definition of bounded sequence, sequence Sm is bounded, that is sequence Sm is bounded, that is sequence Sn is bounded sequence, okay, that is sequence Sn is bounded. This is a proof of our lemma, okay. So from above theorem from above theorem clearly you see that every coordinate sequence is Cauchy sequence and every Cauchy sequence is bounded sequence. So every coordinate sequence is bounded sequence in real number. Okay, so this is a claim for above result. Okay, so next is next theorem or example. Okay, example is if sequence Sn where n runs from 1 to infinity is Cauchy sequence of real number which has convergent subsequences which has convergent subsequence and converges to L. Okay, suppose that sequence Sn is Cauchy sequence and which has a convergent subsequence is given that and which is convergent to L then prove that sequence Sn is also convergent. Sequence Sn is itself, then sequence Sn is also convergent to L, that is which is converges to L. So this is very simple proof. Here given that sequence Sn is Cauchy sequence. Okay, here given that sequence Sn is Cauchy sequence and another is given that sequence Sn has a subsequence converges to L. Okay, converges to L. So how to prove in this theorem? So sequence Sn is Cauchy, therefore we satisfy definition mod Sn minus Sn is less than epsilon. So we choose here epsilon is equal to epsilon by 2. For all epsilon greater than 0 there exists n1 belongs to I. Okay, for n1 belongs to I such that Sm minus Sn is less than epsilon by 2 for all mn greater equal n1, any positive integer n1. Okay, so choosing this and also given that sequence Sn has subsequence is denoted as, suppose that Snk is subsequence and which is converted to L. Okay, which is converted to L, and therefore by definition we satisfy epsilon n definition. Okay, we satisfy epsilon n definition, that is mod Snk minus limit L is less than epsilon upon 2. Okay, so here for all epsilon upon 2 greater than 0 there exists, here choose n2 is any positive integer exists such that we satisfy this condition. Snk minus L, Snk is any sequence but which is a subsequence of given sequence Sn. Okay, so Snk minus L is less than epsilon for all n greater equal n2. Okay, from these two, this suppose that 1 and this is 2. Okay, choose n is equal to maximum of this n1 and n2. If we choosing minimum of this n1 and n2, then for proof of this theorem which does not hold. Okay, because this n is greater equal n1. Okay, so this condition does not hold for given sequence converges for Sn. Okay, and therefore mod Sm minus Sn is less than epsilon for all m and n greater equal n. N is a maximum of this any one number. If n2 is maximum, then m and n greater equal n2. Okay, and n is also greater equal n2. Okay, in this way, and Snk minus L is also less than epsilon for all n greater equal n, and therefore consider mod Sn minus L. Okay, consider mod Sn minus L is equal to take Sn, add and subtract this Sn k, okay, Sn k plus Sn k minus L as it is, minus L as it is, okay. So which implies that Sn minus Sn k plus mod Sn k minus L. Here clearly see that this is a Sn minus Snk. This is a kth number of sequence Sn, and this is nth number of this sequence Sn. So in this way, these are any two number of sequence. Suppose that 1 to up to so on n. This is suppose that n is a nth number of given sequence, and Snk sequence. Suppose that here something here k. So this is a kth number of given sequence, okay. So this is a Snk sequence. Snk is a up to 1 to k, but sequence Sn is a 1 to n, okay. And therefore subtraction of difference of or distance between kth number and nth number, distance between here also, distance between any m and n whatever may be, okay. So taking only m by nk, okay. So therefore distance between two numbers of sequence is less than epsilon upon 2, okay. And this is Snk minus L is also epsilon upon 2, okay, epsilon upon 2. Therefore Sn minus L is strictly less than epsilon upon 2. Therefore for all n greater equal n, we satisfy epsilon upon 2. Epsilon upon 2 is less than epsilon. Therefore Sn is a convergent, okay, and converge to L. In this way find the solution of this sequence, okay. Let firstly write given condition. Let sequence Sn is Cauchy sequence of real number, Cauchy sequence of real number, okay. And therefore by definition, for all epsilon upon 2 greater than 0, here there exists any one number positive integer exists such that we satisfy distance between any two number, distance between two numbers of sequence is very small, but positive, which is less epsilon upon 2, okay, for all n m greater equal n1, okay. Let and also given that which has convergent subsequence. So consider sequence Snk be a subsequence of sequence Sn such that which is convergent to L, okay, such that Snk converges to L, okay. Snk converges to L, that is limit n tends to infinity, Snk has limit is L, and therefore by epsilon n definition, for all epsilon upon 2 there exists n2 belongs to I, such that mod Snk minus L is strictly less than epsilon upon 2 for all n greater equal n2, okay. So choose n is equal to maximum of n1 and n2. Choose n is equal to maximum of n1 and n2. So therefore suppose this is equation number 2 and this is equation number 1. Therefore equation 1 and 2 becomes mod Sm minus Sn is less than epsilon upon 2, where n and m are greater equal n, and mod Snk minus L is less than epsilon upon 2 for all n greater equal n, okay. So Cauchy sequence means, by definition Cauchy sequence, the distance between or difference between two number of sequence, is a very small, epsilon is a very small number, okay. So Sm minus Sn. This is nth number of element is in sequence, and this is nth number. So using this, consider mod Sn minus L. Mod Sn minus L is equal to, add and subtract Snk plus Snk minus L. Okay, so which is less equal mod Sn minus Snk plus Snk minus L. So Sn and Snk is a any two number of given sequence. Okay, this is a kth number of given sequence Sn, and this is nth number. So difference of these two number is very small. So which is a epsilon upon 2, because Sm is nth number. M is a very any one of the number, which is Nk is also. Okay, so there is a strictly less than epsilon upon 2, and this is epsilon upon 2. Therefore, suppose that 3 for all n greater equal n. Okay, and which is equal to epsilon. Therefore, mod Sn minus L is less than epsilon for all n greater equal n, and therefore by epsilon and definition, given sequence limit n tends to infinity, sequence Sn has limit is L. That is sequence Sn. Sequence Sn is converges to L itself. Okay, so this is a proof of our example. Okay, so then next example is let sequence an be a sequence of real number, and for each n belongs to set of positive integer or index set, let Sn is equal to a1 plus a2 plus up to so on an, and sequence Tn is given that mod a1 plus mod a2 plus so on mod an. Okay, and also given that if sequence Tn is Cauchy sequence, Tn is Cauchy sequence, then prove that sequence Sn is also Cauchy sequence. Sequence Sn is also Cauchy sequence. Okay, so how to prove given sequence is Cauchy sequence? Firstly, here not an, here Sn. Okay, so Sn here given that Sn be a sequence of real number for each n belongs to I. Sn is a sum of nth number. Okay, sum of first an. This is an. This sum of Sn is a sequence of sum of this number. Suppose an is 1 to 10, then S1 is 1, then S2 is 1 plus 2 is 3, in this way. Okay, and so Tn is a mod of this term, mod a1, mod a2, summation. And also here given that sequence Tn is Cauchy sequence, and we have to show that sequence Sn is also Cauchy sequence. That is to show that mod Sm minus Sn is less than epsilon. So proof of solution. Since sequence Tn is Cauchy sequence, therefore for all epsilon greater than 0, there exists any positive integer such that mod Tm minus Tn that is difference of any two number is less than epsilon, where m and n are greater equal this n. Okay, so consider mod tm minus tn is equal to mod tn minus tm is equal to mod of tm is a mod of a1 plus plus up to so on mod an plus mod an plus 1 plus plus up to so on mod am. Okay, tm mth number, sum of mth number. Okay, and mth number is a m is greater than n maybe. Okay, so minus, this is completed, minus mod of a1 plus plus up to so on mod an. Okay, tn is a mod an, nth number. Okay, and so this is bracket complete. Okay, and mod here completed. So from this remaining only first nth term are deleting. Okay, because mod a1 minus mod a1 get 0, mod a1 minus mod a2 minus mod a2 get 0. So we get this nth term are deleted. So remaining only in this difference only mod of mod an plus 1 plus mod of an plus 2 plus plus up to so on lastly mod am. These terms are only remaining, and these terms are very less than epsilon, because tm minus tn are less than epsilon. So this term is less than epsilon. Therefore mod tm minus tn mod get separately taken, separately this mod we get less equal mod an plus 1 plus mod an plus 2 plus so on mod am, and this is also strictly less than epsilon. Okay, so this is equation number 1. How to write this? Mod of a1 up to an, this term will get cancelled, remaining only mod of this a b c up to so on. Okay, mod of a plus b plus c up to so on, and this is less equal mod of am plus 1 plus mod of am plus 2. Okay, in this way, and this value are strictly less than epsilon. Okay, now we have to show that what to show here. Sequence Sn is a Cauchy sequence. Now we have to show that sequence Sn is Cauchy sequence. Sequence Sn is Cauchy sequence. Okay, so how to show this? Let mn greater equal n. Suppose that consider mod sm minus sn. Mod sm minus sn is equal to mod sm minus sn is equal to mod of a1 plus a2 plus up to so on an then an plus 1 and up to so on lastly mth number, sum of mth number. Okay, minus sum of nth number. Put the value of sn is a1 up to so on an in this way, and this is a mod. Okay, so taking value is a1 minus a1 get 0, a1 minus a2 get 0 up to an. First nth term are get 0, and so remaining only mod an plus 1 plus mod an plus 2 up to so on mod am. Okay, so mod of a plus b plus c up to so on, which is less equal mod an plus 1 plus mod an plus 2 plus up to so on mod am. But this value is strictly less than epsilon. Okay, from 1 this is less than epsilon, and therefore mod sm minus sn is less than epsilon for all mn greater equal n, and therefore by by definition of Cauchy sequence, sequence Sn is Cauchy sequence. Sequence Sn is Cauchy sequence. Okay, so this is a proof of our example.